So we'll now move on to the Doppler effect, so a fairly famous effect used. And how it works is that as an object moves, the sound wave that it travels, or as it's traveling with some speed, the sound wave actually differs. So normally if you're sort of a static object emitting sound, then these crests will be evenly spaced apart. I know it's not clear on that diagram, but they should be. But if you're moving, then due to a conservation of energy, some of the sound waves will cluster up here, and some others will be sort of very far apart as you're moving. And this phenomenon is known as the Doppler effect. So the crushing of these sort of wave crests towards each other. Technically, the definition is the apparent change in frequency as the source moves. And this is actually very applicable and happens a lot in real life. So if you've been waiting at a bus stop and an ambulance passed you, then you would have noticed that as the ambulance comes closer to you, the frequency of the siren gets a lot louder. And as it goes away, it dissipates or sort of decreases. Now, this happens with all kinds of waves. So it happens both with sound waves and with light waves. We'll get onto how it works with light waves once we've finished two different examples of the Doppler effect in terms of its maths. And the formula for it is this. So f prime is the frequency that we're perceiving as the object is moving. F is the actual frequency. C is the speed of the wave. And v is the speed of the object. Or I sort of did it a bit verbose here. It's the relative speed between the observer and source emitter. Now the key thing that I have to note is this plus or minus in the middle. So if the source is moving away, the frequency increases. So the bottom should read C minus V if it's moving towards the observer. And if it's going away from the observer, then the bottom reads as C plus V. So we'll be doing two different examples of using this formula in different capacities in the next two videos.